Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
PhD a few months ago in Hebrew University of Jerusalem, and he's now at Cat.
So I will talk about online ascending auctions for gradually expiring items, and this is a joint work with Noam Nissan. So in our model, we have M items, and all the items are identical, except for the fact that they expire at different times. So without loss of generality, item 1 expires at time 1, item 2 expires at time 2, and so on. And we have players, and players arrive over time, and each player desires exactly one item between his arrival time and his deadline. So for example, player 1 and player 2 both arrive at time 1, and player 1 has deadline of 3, so he wants either item 1 or item 2 or item 3. And player 2 has deadline 1, so he wants only item 1. And that's what we see at time 1. Then we make some kind of a decision, of an allocation decision, what to do. And then at time 2, we see that player 3 comes. Player 3 has deadline 3, so he wants either item 2 or item 3. And each player has a value for receiving one of his desired items. So this value is Vi. Yeah, so it's the same value, yeah. So he receives the value Vi if he gets one of his desired items. And the point is that all the parameters of the players are secret information. Only the players themselves know the parameters. So no one else besides the players know the arrival time of the player, the deadline of the player, and the value of the player. And the players won't necessarily reveal to us their true parameters because their aim is to maximize their own utility. They are selfish. They want to maximize the value that they obtain from the auction minus any price that they have to pay. And our goal, in contrast to this selfish behavior, our goal is some global goal. We want to maximize some global parameter. Here we want to maximize the sum of true values of the players that receive an item. So we want to implement some global goal, but the players act selfishly. Each of them has a selfish goal. And this is the contrast here. Yes?
Is there a real-world scenario that you have in your head when you think about this model?
Okay, good. So that's a good question. So you can think both of economic scenarios and computational scenarios. For example, you can think of bandwidth allocation in a network. So you have bandwidth, and you have to allocate the bandwidth for the first hour, for the second hour, for the third hour, and so on. And you have to think what to do. Or perhaps a more concrete example is, theater tickets. So I'm in town for, say, a week, and I want to see a theater show. And they have a theater ticket for today, theater ticket for tomorrow, and so on. There are many examples that you can think of.
Even for some extent, airline tickets.
Yes, airline tickets.
Maybe
Yeah.
I want to fly on a given day, but I thought when I buy or so,
Yeah.
people play games by
Yeah.
buying later or earlier
Yeah.
to try to get.
Yeah, you can think of many applications. Exactly. Actually, I wrote here transportation tickets, thinking about something similar. But let's keep in mind the general model in which you have items and they expire at different times. And then the question is what to do about it.
Well, also for ad auctions, you could think of this, except, I mean, being who we are, we might want to like maximize the revenue rather than
Right. Okay, that's a good question. We chose social welfare because it was easier. The problem is hard as is. So to do it with social welfare is easier to do it with revenue.
You have at least thought about the revenue maximization.
I thought about it a little bit, but I don't have anything to say about it.
Items are expiring, meaning that you have fewer items.
Yes, the number of items is fixed. Yes, you have M items, you know that in advance, and you have to, yeah.
And you know the expiration time.
Yes, you know. Yes, that you know. Yeah.
Item
It can be allocated before time I, but not after time I.
It can be allocated before time.
Yes, yes.
Given to someone who wants it before time.
Yes, yes. You can do that, although, yes.
So this is different from the application.
I prefer, perhaps we can, yeah, I prefer to postpone the discussion about the specific examples to later on, and just to concentrate on the general model. Yes. Sorry?
Wafer style behaves just like airline tickets. You don't should behave very much the same thing. You want to order them ahead of time.
Oh, okay.
Okay. Yes.
So with the airline analogy, the analogy would be you have a single flight here, optioning often is one seat available.
So let's postpone all the relation to practical examples to later, because I'd like to get along with the.
Oh, well, and by the way,
Uh-huh.
you have until 3 o'clock.
Okay.
And we expect, and the reason that we give you a little extra
Uh-huh.
time is because we do interrupt constantly.
No. Interrupting is
We're being
great.
rude, we're being
Okay, no, that's okay. Interrupting is great, but yeah.
Right.
Just a model, not
And we're
application.
relentless,
Yeah.
too.
So,
Okay.
so you allocate ahead of time.
Uh-huh.
But, I mean, so wasn't your model that player I wants it between a certain
Yeah,
time?
so
what does it have to give him an item which is after the time expired?
No, you have to give him. So you have to give the player an item between his arrival time and his deadline. This is part of the model. But
Do you know it in advance?
oh, so that's okay. So I misunderstood your question. So you cannot allocate item 4 to player 1. No, this you cannot do. No.
And
Okay.
at time
Okay.
1, you can't
No, so I'm sorry.
allocate item 3 to player 3 because you don't even know that player 3
Yes,
will come.
yes.
You don't know when they, I mean, it's
Yes.
online.
Exactly. Yeah, exactly. So it's online. So it doesn't make a lot of. If you're talking in the worst case, it doesn't make a lot of sense to allocate item 3 already at time 1, because then you could be very, very worse off in the future, because at time 3, suddenly you realize that somebody with a very high value wants item 3. So, okay. Okay, so that's the model.
The expiration part of the model
Yes.
is saying that if it's time 2, you can't get item 1.
If it's time 2, you cannot get item 1
Item one
anymore.
is gone.
Yes.
Gone.
Yes, it's gone.
And that's what you mean by expiration.
Yes, exactly. Yes. Okay, so first let me say a few words about the algorithmic status of this problem. So it's a well-studied problem. It is actually equivalent to scheduling of unit jobs. And in the offline case, if you know everything in advance, then it has a matroid structure, so it can be solved optimally in polynomial time. And in the online case, when one doesn't know the entire sequence in advance, then there is a lower bound of about 1.6. So there is a lower bound on the approximation ratio of about 1.6. So we cannot hope to achieve better than 1.6. Sorry?
Is that also for randomized algorithms or just for
No, actually there is a randomized algorithm that achieves E minus 1 over E. But I'm not.
Which is what relative?
Sorry? Yeah, it's 1.57, I think. Yeah, something like that. Yeah.
And when you say fully time computational, is that feasible? So is it quadratic or linear, or is it some?
No, it's feasible. I think it's quadratic, but I'm not sure.
It's easier than magic, right?
Yes, it's easier than matching. Matching is, yeah. Yes, it's much easier than matching, yeah. And so in the online setting, we cannot do better than 1.6, and the following simple greedy algorithm obtains a 2 approximation. So at time t, you just look at all the players that are there and just allocate the item t to the player with the highest value at time t. But this is an algorithm that requires, of course, from the players to be completely obedient, to reveal to us their true parameters, their arrival time, their deadline, their value, and then we can do 2. But in our setting, we assume that players are selfish. So we want to somehow motivate them to reveal their true parameters to us. So how will we do that? So the most popular approach in designing algorithms that motivate the players to reveal their true parameters is to design truthful auctions. This notion means that the players are motivated to reveal to us their true parameters by the following strong argument of dominant strategies. No matter what the others are going to do, player I will maximize his utility by simply revealing his true parameters. So this is kind of a worst case argument that sounds very strong. And quite surprisingly, there are many recent positive results for truthful auctions. So although it is strong, it is still accomplishable in some settings. However, in our setting, we cannot design truthful auctions. We show that any deterministic truthful auction for our allocation problem cannot obtain an approximation ratio better than m, where m was the number of items. Specifically, so we say that an algorithm approximates. So actually, I didn't understand the question. What is by an approximation ratio?
What do you approximate?
Okay, so our goal is to maximize the sum of values of players that received an item. So that's our goal. And there is an optimum, because
So you compare to the offline optimum.
some of the true values, yes.
And you compare it to the offline optimum?
And I'm comparing it,
The online optimum?
no, I'm comparing it to the online optimum. No, to the offline optimum.
Okay.
Yes.
So that's a sense.
Yes.
So,
No, I'm comparing
approximate means approximate relative
to the offline optimum. Yes.
Yeah, what is
How
that?
that already just
So m is the number of items. M is the number of items, yes. So specifically, there's no constant ratio approximation. And actually, the approximation, if you want a truthful auction, it's a deterministic truthful auction, it's quite poor.
So what is the simple truthful M approximation?
So you can do the following auction, which is truthful. At time one, look at all the prices. So you ask, whenever a player comes, you ask him to reveal to you his parameters. He might lie, but we'll see that it's truthful to reveal his true parameters. So once you have the parameters of the players, you ignore the deadlines, and at time one, you just allocate the item to the player with the highest value, and charge him the second highest value. And then at time two, you set a price for item two, which is equal to the maximum. So sorry, let me start from the beginning. So at each time t, you set a price for item t as follows. You look at all the previous values up to time t minus 1, and this is a threshold. And additionally, you look for player I, you look at time t, you look at all the values of the other players at time t, and the price for player I is the maximum between these two numbers, either the maximal value of all the players that arrived earlier, or the other players at time t. So so that's truthful. Yeah, but this is an M approximation because the player with the highest value will get an item. So the player with the highest value will get an item, and you cannot do better than m times the highest value because you have m items. So that's okay. So yes, yeah. So that's without loss of generality.
Maybe it's better to say rather than because this is only a time. Doesn't exist before time I.
You can think of it as it exists even before time I.
No, but
But you can only allocate it at time.
No, you can allocate it also before time I.
You can, but
you
people
can't
to
use
someone
it.
who wants it.
you
Time
can't
I.
use it until time on.
So what's the point of allocating it before? It exists only at time I.
Okay.
You advance that it will exist, but it exists only at time I.
I have to think about it. I have to
It's
think
like it
about
has to get baked and then it's spoiled.
it. Yeah.
I mean,
Perhaps I have to think about it.
And in every step, you allocate only one item to one person, or you can say
So the point is as following.
Or if it expires at time I, you have to allocate at time I. But
You can allocate it, but you must give it a time.
Right, which is why Ori is saying
Time
he
I.
finds it least confusing to
To say that it exists at
that
time
it
I.
exists at time I. You can allocate for the future, but it exists only.
But
Okay.
it's a theater. I mean, you can't. Maybe the ticket exists, but the theater show only.
Oh, is on time I. That's perhaps I have to think about it. I'm not sure because I thought about it at the beginning and I have to think about it to verify if you're right. Yeah.
If you
Yes.
found the ratio of the maximum bit to the minimum bit,
Uh-huh.
you get what's the best factor?
So you can get a log of Vmax over Vmin. I'll talk about it at the next slide. Yeah, but first, Kunal has a question.
Does the lower bound hold also for randomized algorithms?
No. So it's only for deterministic algorithms. That's a good question. I don't know about randomized algorithms. Yes, that's a
But
good
do
question.
people believe there's an offline, I mean, 1 plus epsilon approximation, randomized?
Randomized.
Online or?
There are several. You should separate several things. First of all, there is the online problem without any relation to the strategic behavior of the players. In this case, there is a lower bound of 1.6 for deterministic algorithms, online algorithms, and randomized algorithms can perform better. And I'm not aware that there is any lower bound for randomized algorithms. That's for the case of the online scenario without any strategic considerations.
Offline without. Okay.
Yeah, when you add strategic considerations, then nothing is known. So I don't know.
Yeah, they keep saying.
No, but
And they
off,
say line
no, but offline also people laugh.
Sorry, I didn't. No, I didn't.
He's saying offline you can do a VCG method.
Yes, because you know because the optimal allocation is polynomial time computable, you can do the VCG mechanism. Yeah. The offline problem is completely solved. Yeah, the problem is the online problem. Yes. Okay, so we have a So we have a problem. We want to handle the case where the players are strategic, but we cannot design truthful auctions. So the question is, what can we do? So there are several ways to approach this difficulty. The first way is to relax the equilibrium notion and to consider a Bayesian Nash equilibrium, to assume distributional assumptions over the players, and then and also to assume that all the players know the underlying distribution, and all the players know that all the players know the underlying distribution, and so on. So those are very strong distributional assumptions.
So it's not that you're saying there are strong assumptions on the class of distributions, which could actually
Yes. I'm saying that there are strong assumptions about the way that players believe
have
and
knowledge,
yes.
But if you
Yes.
bought all those, and you may not, then you could probably do it for a wide
So-
class of
But how is it
So that's a good question. Actually, perhaps we can talk about it also in a sequence. Sorry? So in the notion of, usual economic work on this, the usual thing that they do is they assume an underlying distribution. I don't know, Poisson arrival times, uniform values, uniform distribution over values, and something like that. And then they assume also that all the players know this underlying distribution. And then they are able to construct Bayesian Nash equilibria.
Then the
But-
players don't have any free will because
They have, because you force them to believe on this distribution.
Not only you force them to believe, but you also force them to actually
to not
obey.
violate that distribution.
Oh,
No. The parameters of the players are they are given. The parameters are given to them from an outside source. The parameters, there are three parameters. There are arrival times, deadlines, and values.
I see. So, for example, if I made a distribution which was a delta function at some price, the players could still lie, but the other player knows that the true value is a delta.
Yeah.
No,
That would be a particularly trivial case.
No, the players don't know the true parameters of the other players. They only know a distribution over the true
Right, but
parameters.
if the distribution is a delta
Ah,
function,
okay.
that happens to be
Okay,
extremely
okay,
They would
yeah.
still be allowed to lie.
No, but usually,
Okay.
No, but that's the setup,
Our
right?
talks
the
are interactive, Ronnie.
No, that's okay.
distribution is fixed, but I can lie about what you have sort of some guess. What
So this is not my setup. So so I'm just mentioning it so that to make a difference from other possible setups. So
And we'll come back to the question of what distribution.
I won't.
Maybe if you get time.
Maybe he
Which
doesn't
you
even
probably
use
won't.
it.
No, I don't have an answer to the question, but I can exactly. But I prefer to exactly discuss it on an appropriate place in the talk. I don't. Okay. No, I don't have an answer, but but you'll see. Okay. Okay. So that's the first thing that we can do. The other thing that we can do is to add assumptions about player types, and then to be able to come up with truthful auctions. For example, if we assume that the values are drawn from, if the values are in between Vmin and Vmax for some known Vmin and Vmax, then we can have a randomized truthful auction that has an approximation ratio of log of Vmax approximately.
Who is VSV?
So it's Blum, Sandholm, and Zinkovich from CMU.
Is it Manuel?
No, it's Avrim.
It's out.
Yes. So, so that's another possibility that we can do. However, this is both randomized auction, and also it has additional assumptions on players, and also it depends on the range of the valuations, and it seems a very high price to pay with respect to the deterministic two approximation that we know to exist if we don't assume any strategic behavior.
There's something I don't understand. You sure you mean you don't have max over Newman?
Yeah, that's a good question. I looked at their paper, and it's V max minus V min.
What if the difference is smaller than 1?
Yeah, no, you're right. It's possibly V max over V min. Yeah, you're possibly right. Yes.
Yeah, that would make sense.
Okay, I'm not sure. It's approximately log V max if V min is
So
1.
it's written in some paper like that.
Yeah, in the paper it's like that. Yeah. Yeah, and actually I was convinced it is this, but yeah, but lately several people asked me that, so I'm not convinced anymore. I should check it again. And another thing that bothers us in that auction is that the way that it works seems somehow artificial. They choose a price according to some very complicated, sophisticated distribution, but then all the items are sold at that particular price. So it seems a bit bothering that prices don't change over time according to the number of players that exist and so on. Yes, it's a similar idea. Yeah, actually, Azar, Averbuch, and Marson generalized this too. Yes. You're right. Right. Okay, so instead, we don't take this approach either. What we do instead is that we relax a little bit the notion of equilibrium, but we keep worst case analysis. We don't assume any distributional assumptions, and we also don't assume anything else about the types of the players. So what I'm going to do for the rest of the talk is to describe the positive results. I'll first describe two ascending auctions that seem natural in this setting. I'll discuss their algorithmic properties. And by this, I will also try to give an intuition to an equilibrium notion that fits well. And then I'll describe more formally this new notion of equilibrium. I'll discuss its properties. It has advantages and also disadvantages. And then I'll state the main theorem and try to give you also some intuition for the proof. Okay, so the first auction that we define is the online iterative auction. It is a natural adaptation of the iterative auction of DeMange, Gale, and Sotomayor for this online setting. And this auction works as follows. I'll describe it and then I'll give an example because I know the description here is a bit confusing. So I'll describe it shortly and then I'll give an example. So in the online iterative auction, we have a vector of prices and a vector of temporary winners that we keep at all times. So even at time 1, we have a price for item 1, a price for item 2, and so on, and a set of winners for item 1, for item 2, and so on. And we update those prices and temporary winners according to the following iterative process. We approach to each player, and we ask him to place his name on some of the items. If he places his name on an item, then the previous winner, the previous temporary winner is deleted. He is now the previous temporary winner, and the price goes up by some small amount delta.
So he chooses which item?
Yeah, he chooses which item. Yes, yes, yes. Yes. And then we move on to the next player, and he puts his name somewhere, and then we continue. And we do it iteratively in a cycle until no player wants to place his name. Then the phase of time t ends. We allocate item t to the current winner of time t for the current price. We keep the prices and temporary winners, go to time t plus 1, and new players might join, so this process continues. So let me do an example. Only on one, yes. You're allowed to put your name only on one. If your name is already on one, you're not allowed to put your name on another. Yes.
So you're not allowed to delete yourself from one?
No, you're not allowed. No. Once you're there, you're there. Yeah. Yeah. So let me do an example. So suppose we have 2 items, then we have 3 players. Player 1 has a value of 3, and he has a deadline of 2, so he wants either item 1 or item 2. And player 2 has a value of 5, and also a deadline of 2. And player 3 has a value of 2 and deadline of 1, so he wants only item 1. So let's see what happens. First, we approach to player 1, ask him, where do you want to place your name? So let's say he places his name under item 1, or above item 1. Then we approach player 2, and he places his name above item 2, and the price goes up. And then we approach player 3. He has no choice, so he places his name above item 1. And then we go back to player 1. And let's say that player 1 chooses to place his name again on item 1, although notice that the price of player 2 is smaller than the price of, the price of item 2 is smaller than the price of item 1. So that's what happens, and now what happens, the auction ends because player 1 and player 2 are written there. Player 3 doesn't have anything to do anymore. So player 1 wins item 1, he pays 2. And what will happen with player 2? We don't know. This depends. Sorry, is there any question?
I understand that, but I don't know what's going to happen. I don't understand why player 2 doesn't just get.
Okay, so exactly. So player 2 depends on what will happen at time 2.
Oh, that's
so
right.
yeah,
Okay.
so that's time
Only
1.
Time 1 is
Yes,
time
yes.
1.
The example, yes. The example is at time 1.
That's why player 1
Exactly,
paid
and that's what. So exactly, exactly. So both of them took risk. Player 1 took a risk because he was afraid of what is going to happen in the future, so he insisted on item 1. And player 2 took a risk. He preferred the lower price, so he kept himself on the other hand of the scale. Yes. So. Great. So that's a good question. So the way that I told the way that the example is built is just first of all to verify that you understand this online iterative auction, and second of all that you understand why does the players might have different considerations about how to behave. So you can think of it as if the players did that and we don't know why yet. So let's try to analyze why they behave as they behave. This is also possible, but
is he allowed to enter the auction later?
He's allowed to enter the auction later, yes. That's the way that I wrote it, that is defined, yes.
Player 1 could have switched from item 1.
No, he can't.
Okay,
Once he's stuck. Unless someone will delete him, and then he will be able to place his name.
Take yourself off.
No, you can take yourself off, but if somebody deletes you, you can write yourself wherever you like the next time.
Want to bid on a certain item to find out how much whether you are willing to pay more.
Yes, you might. Okay, so you might. So the best way to understand, I think the best way to understand how will players behave is first to analyze the offline case in which all players arrive at time 1. So that's the definition of an offline case for the moment. So think of it like this. So all the players arrive at time 1, and they know that no one else will arrive in the future. So what happens in this case? So this case was exactly the case that, not exactly, but this case is a special case of the case of the Mange, Gale, and Sotomayor. So they defined the following. A player is myopic or behaves myopically if, when he is approached, he always writes his name on the item with the lowest price. So he looks at all the items that interest him, he chooses the one with the lowest price, and he writes his name there. So if he behaves like this, then he is myopic. And they have a theorem that says that if all players arrive at time 1, and if all of them behave myopically, then this online iterative auction finds the optimal allocation, reaches the exact optimal allocation. And second, if all the others behave myopically, then player 1 will maximize his utility, player I will maximize his utility by behaving myopically. So myopic behavior forms a Nash equilibrium.
Delta was the amount.
Yes, delta is the amount at prices. You can think of it as very,
He said one now.
yeah, just so the example will finish quickly.
What is
Sorry?
what does the
Delta is
optimal
equal
output?
to an
No, I know what delta is, but what
So this is not formal because okay, but so you can think of it as,
You get within.
Yeah, I
the
prefer-
Optimal allocation or what? Like
so actually it's not even delta. I think it's m times delta or something like that. So delta is the amount in which the prices are increased. So as delta goes to 0, this auction goes to the optimal allocation. The allocation reaches the optimal allocation. So-
distributed at the end is at most m times
Yeah, it's
delta.
minus. Yes. The difference is m times delta less. It's at most.
Player
Yes.
is just delta or is it m times
Sorry, I didn't understand the question.
Item,
Layer.
delta per item.
delta? It's delta per item.
It's delta per item. Yes, exactly.
So,
Yeah.
so I could sort of game system get maybe delta.
Yes,
more.
exactly. So both, yeah, you're completely right. So both the optimal allocation varies by m times delta, and also, and also the players can improve their utility by delta. Yes.
So then being myopic in this Nash equilibrium,
Yes.
if I know everybody is myopic, I'm better off with
Yes. You're right. So myopic behavior is a Nash equilibrium. Yes, ex post Nash equilibrium. Yeah. Yes. So, but this is in the offline case, and actually, I'd like to give you some intuition to the proof because it will help us later on. So first of all, let's try to understand the basic structure of allocations. Everything is very simple, so that's why I can do it here. I mean, so let's look at the optimal allocation. So I'm writing it the following way. So below the line, I'm writing the item numbers, 1, 2, up to m. And in the cells themselves, I write the names of the players that received that item in the optimal allocation. So player J, for example, received item D in the optimal allocation. And the unit here, the object here that interests us is what we call a tight block. So a tight block is a subset of the players. It has D players, and all of the players has deadlines at most D. So there are D players. Each one of them has a deadline of at most D. So they must all be located at the prefix of this allocation. So we have many tight blocks, but they are all prefixes. So they are contained one in the other. And the specific tight block that interests us is the minimal tight block, F for first. So we have a lot of tight blocks. Okay, good. So great. So the set of players B is not a tight block.
Wait, what is DJ?
It has to be exactly.
Yes, exactly.
D of J
No. It's
deadline of player J.
Oh, DJ is the deadline.
yeah. D of J is the deadline of player J. Yes. So perhaps I will repeat it. I will repeat the definition. Yeah, thanks. So this is the way that you should imagine the optimal allocation. And what we are interested in is in subsets of the players written here that have the following two properties. The subsets B have the following two properties. The first property is that they contain D players. So a subset B, which we call a tight block, contains D players, and every deadline of each player in B is at most D. So we have D players. All of them have deadlines at most D. So none of them can be located after D, so they must be in the beginning of the optimal allocation S. So they are a prefix.
The players that are in the optimal allocation. So
Yeah. I throw away all the others. Yeah, I'm just trying
these
to
are,
analyze.
These type blocks are the blocks that if you focus on them, then it's not affected by the later.
Exactly.
They don't affect the later steps. So
Yes.
then you get the conditional independence that you need.
Something like that.
Yeah.
Something like that. Yeah.
So
Yeah.
that's
So
why you're-
yeah, but let me do it slowly. Yeah. So we know that type blocks are prefixes, and they are contained one in the other, and we are looking at the minimal type block. All the players in B are located in the beginning of S, because we have D of them. We have D of them, and they all have deadlines at most D. So they cannot be located after D, and they are exactly D of them.
a prefix.
Ah.
You just meant in the
Okay.
beginning.
In the beginning, yeah.
Okay.
Yeah. And we look at the minimal type block, which is the type block that doesn't contain any other type blocks, and we call it F for first. And the point is that the nice thing about minimal type blocks is that every player J in the type block can be located first in the optimal allocation, because we can do the following switch. Let's see how the player J can be located first. So let's find some player among the first D-1 player who has deadline D. There is such a player because otherwise the first D-1 players were also a type block. So we can switch between J prime and J, and we can do that on and on until J reaches the first place. So every player in the minimal type block can be located first, and therefore the social cost of every player in the minimal type block is exactly the highest unallocated player outside. Because if we take out any of the players of F, we can instead insert to the optimal allocation the player with the highest player with the highest value that was not allocated. So that's I star, and this is exactly the VCG price, if you know what is the VCG price, and if not, this is the definition of the VCG price. Sorry? What was the question? I didn't.
Say you look at any other player that was not allocated.
Yes.
If this particular player wanted only times per time.
So I'm looking at the optimal allocation for the offline problem.
Yeah.
Yeah. So
They all arrive at time.
Right.
yes,
That's what he meant by
yes.
offline.
That's what I'm defining by offline. Yeah.
Okay, offline.
Just because it is. Yeah. Just to make things.
There's another version of
You're right.
you have all the information at time.
Yes. Yes. You're right. It's somehow misleading to call it like this, but still.
Not the one that is static
Yeah.
Right.
It's not the same.
It's the problem of looking at time one. Suppose nobody else comes after time one. So that's exactly a special case of the problem that we study here, when all players arrive at time one. Yes. Okay, so. Uh-huh.
Or they announce that their start time is time 3, but they tell you at time 1. So it means
So.
we mean the first thing,
Right.
that their start time is time 1. Every player's start time
Right.
is time 1.
Yes.
AI
Yes.
equals 1 for all I.
Oh, that's
Yeah.
an interesting question. When you do truthfulness,
Yeah, but then I'm not talking about truthfulness yet.
but now
Oh.
the question back to the
Uh-huh.
definition.
Uh-huh.
In your setting, does truthfulness mean that I have to tell you my true arrival time, leaving time, and price at my arrival or at the beginning of the day?
Truthfulness means that it is a dominant strategy for you to reveal your true parameters
When? Do I have to tell you
on your arrival time.
on my arrival?
Yes. Okay, so that's the structure of allocations, and now let's see why this iterative auction reaches the optimal allocation. So what I'm claiming is that, first of all, that all the prices of the slots in the minimal type block will always be the same prices throughout the auction, assuming the delta is very small. Assuming the delta is infinitesimally small. So for example, let's see why the price of J prime and J double prime will always be the same. So because they are behaving myopically, the price of J double prime, so first of all, the price of J prime won't be larger than the price of J double prime, because J prime can always write himself in the place of J double prime. And on the other direction, the price of J double prime won't be larger than the price of J.
J prime is already committed.
Yeah, you're right. Yes, you're right. But think of it as very, very, yes.
What was the answer to that question?
The answer is that ignore it.
No, but.
No, the answer is that I cannot.
At the time J prime wrote its value, at that time already this
Ah, thank
he
you.
could have wrote
Okay, he could have already written into slot 1.
Yeah.
at that time.
Okay, yes, that.
Yeah. And the other way around, also, the other direction also follows from the fact that J double prime has deadline
Afterwards, so he got a
afterwards.
chance.
Yes, yes,
So
yes.
they both
Exactly.
got a chance to overwrite each other.
Yes, exactly. So what?
And they did.
Yes. So what happens here that so there are D plus 1 players all want. You can think of it as all want this slot, that's minimal slot F, and the prices the price of this minimal tight block keep rising until this highest unallocated player doesn't want to participate anymore, so he is left outside. So the price, yes, so the price of all the players here is exactly the VCG price. Yeah. So okay. So this is what happens in the offline allocation. And now let's talk a little bit about what happens in the online allocation. So in the online allocation, we cannot assume that players will want to behave myopically because they might fear of the future. This is exactly what the example showed. So it is a completely reasonable behavior to behave differently than being myopic. So what we define is that the player is semi-myopic if he always bids on some item with price lower than his value, not necessarily the item with the lowest price. So a player is semi-myopic if when he is approached, he always places his name on some item.
How can he be worse than semi-myopic?
So, for example, he can decide to go to the movies and because he has a very high deadline and show up close to his deadline. So that's one behavior which is not a semi-myopic.
Just to
Yeah.
to wait.
Yes,
To defer any
yes,
decisions.
or to write your name after your deadline for some reason. I don't know. For some reason, yeah. Okay, so but semi-myopic. So we rule out these kind of behaviors by a semi-myopic behavior, but all the other behaviors, and especially all the behaviors in which players may be aggressively towards the first item because they are afraid of higher arrivals later on, or the completely other extreme, are all captured by this semi-myopic definition. And the theorem says that if all players are semi-myopic, then the online iterative auction obtains a 3 approximation. So this is for the online iterative auction. So I'd like to talk. I will talk a little bit about this theorem. Yes.
What's the incentive for somebody to bid on something at the central time period? I mean, you're forcing them to do that, and there's some incentive.
So in the offline scenario, indeed nothing will happen in the second period, but in the online scenario, new players arrive, so they are not written, but they might have high values, so they.
You're not going to assign the item until time 2, and what's my incentive to bid on time 2?
At time 1?
At time 1.
Okay,
Which
so
you're forcing me to do.
yeah, which I'm forcing to do. Okay, so that
So I'm revealing information.
great. Great. So that's a good question. So your incentive to bid for item 2 at time 1 is to prevent competition in the future because very low valued players a very low valued player received item 1. So if you do not compete for item 1, then the other player that is interested in item 2 might be written down for item 2, and both prices will be low. And then at time 2, you will suddenly find out that you have a very high competition for item 2. Still, both of you could have gotten items 1 and 2. So there is an incentive, but your question is absolutely has a lot of meaning in the sense that it's not clear what is the incentive of players to be semi-myopic, and I'll talk about it in the sequel. But for now, this is the definition, and this is the theorem. If they are all semi-myopics, then the online iterative auction obtains a 3 approximation. Okay, I'll talk about the proof of the theorem shortly, but after I'll talk about a second type of an auction, that initially seems very different, but turns out to be very much, turns out that it has very much the same structure as the previous auction. So in the sequential Japanese auction, this is the second auction, item T is sold at time T. So you know what? How much time do I have until 3 or I have until
3.
Okay.
Is that okay?
I'm just thinking perhaps if I should just skip this part. Okay. Okay, because okay. No, it's nice that there are a lot of questions, but then I didn't anticipate the pace. Okay. So okay, but I'll do it. Yes, I'll do it. Okay, I'll do it quickly. So.
And then we'll slow you down.
Okay.
Maybe go a little beyond.
Don't slow it down with non-questions.
Okay. So I'm slowing down already. Yeah. So in the sequential Japanese auction, item T is sold at time T using a classic simple ascending auction. So we don't look about the futures. We don't have prices for the future. We don't have anything about the future. We just sell item T at time T using an ascending auction. So the auctioneer raises the price. Everybody at the beginning raises their hand, or some of the people raise their hand. And as the price ascends, they can lower their hand. The price stops when exactly one person has its hand up. He wins. He gets the item for this price. And then at time T plus 1, we start from the beginning, and so on. So
Is that different from English?
yeah. So that's English. So yeah. So that's in the literature they have this. Yeah, they have this discussion. What is the difference between Japanese and English? In English, the players themselves can decide how much they raise their values. So I'm saying I raise it to.
So you're doing the increments.
Yes, and then you have to analyze strategies a little bit
And
differently.
once you drop out, you can't come back, right? Whereas
Yes.
In English, you can drop out and come back.
No.
That's irrational.
No. English.
Because you don't want people to learn your price.
So also in the English auction, it's common to assume that you cannot come back after you drop. But here you can come back at time. Okay, so that's the auction, and let's do an example again to clarify things. So we have the same set of players, and let's first analyze what happens if players 1 and 2 independently, they both decide to behave in the following very strange way. So suppose that they decide not to participate in the auction of item 1, exactly like you asked, and just wait for item 2. So what will happen? So at time 1, they don't participate. The only player that participates is player 3. So, he will win. He will pay 0, player 3. And player 1 will certainly not win because player 2 will always outbid him. So player 1 won't win. Player 2, we don't know. He might win. He might not win. Depends on what will happen at time 2. So this is what happens if both players decide not to participate at time 1. And now consider a different kind of behavior. Suppose that both of them, player 1 and player 2, both decide to participate in the auction, but only until 2 players remain. And the number 2 is because each of them wants 2 items. So they participate, but not until they win, but until 2 players remain, exactly 2 players remain, or until they win, whatever comes first. So let's see, I will justify it later on, but let's see first of all what happens if both of them decide to behave in this way. So the price starts at 0, and when the price is very low, then none of the players drop, because player 1 won't drop because there are 3 players in the auction. Player 2 won't drop exactly because of the same reason. Player 3 won't drop because he has nothing to lose from staying. So the price keeps going up until the price reaches 2. When the price reaches 2, player 3 wins. When the price reaches 2, I'm sorry, I was confused. When the price reaches 2, player 3 drops because the price reaches his value. He can't gain anything by staying in the auction. And then both players 1 and 2 drop immediately because of their decision to drop exactly when 2 players remain. So one of them will win, either 1 or 2, we don't know. The winner will pay a price of 2. The other one might win at time 2, might not win at time 2. This depends on what happened at time 2. Okay, so that's what happens. And as before, it is first very useful to analyze the offline case. And surprisingly, for the offline case, again, we have a notion of myopic behavior that leads to the optimal allocation as well. So a player is myopic, we define that a player is myopic at time t if he exactly drops when the price reaches his value or when d minus t other players remain. And the intuition for this d minus t other players that at this price level, because he knows no other player will arrive in the future, so at this price level, he knows that there are d minus t other players that compete with him. So for sure, he will get the item at this price level. Because he wants d minus t items, only d minus t other players compete with him, so there's no point in staying further, and so because the price comes up. And the theorem says that if all players arrive at time 1 and they are all myopic, then the sequential Japanese auction finds the optimal allocation. Let me just, so the proof here is very similar to the proof in the previous case, but I will skip this slide, I think. Sorry?
The prices of items,
They are, yes. The prices are exactly the VCG prices. So you can show, yes, the prices here are also, actually the prices are not exactly VCG prices. If you include a slight modification to this auction, they become just tie-breaking, or more delicate tie-breaking rule, then the prices become VCG prices, and then they are decreasing. So the prices of all the players in the first minimal tight block are exactly equal to the highest valued player. In the second minimal tight block, something similar, and so on. Okay. So let's now see what happens in the online case. So again, in the online case, we cannot claim that the player will always be myopic, because again, he might have an incentive to be more aggressive in earlier time periods because he's afraid of what will happen in the future. So we define a player to be semi-myopic if at any time t he drops not earlier when d minus t other players remain, and not later when the price reaches his value. So he has a range in which he can drop. And the theorem also says, in parallel to what the previous theorem said, that if all players are semi-myopic, then the sequential Japanese auction obtains a 3 approximation. Okay, so just as a word of warning, some people told me that it's too confusing to keep both auctions, to keep focusing on both auctions as the talk continues. So you can choose either one of the auctions, the one that you prefer best. So we have myopic behavior in the online iterative, and also myopic behavior in the sequential Japanese, and also semi-myopic behavior. And we do this overloading on purpose because all the theorems and all the structure is very similar between these two auctions. So just pick one of them and concentrate on that one until the rest of the talk. So I'd like to say a few words about how do we prove this 3 approximation. So the way that we prove it is by analyzing a family of algorithms and showing that all the algorithms in the family obtain a 3 approximation. And we call this family of algorithms semi-myopic algorithms. And again, I will talk a bit about why we do this overloading of names in a moment. So for now, forget about players and strategic behaviors and just think about algorithms. So if we want to solve this problem, we can think of many different algorithms to solve the problem. The greedy algorithm, in which the player with the highest value always gets the current item, is one extreme of the family of algorithms. In the other extreme, you can find the myopic algorithm. In the myopic algorithm, at each time t, you compute the optimal allocation according to the current set of players, and you allocate according to that. So you allocate, so in the myopic algorithm, you allocate according to the current best allocation. So at each time t, you see which players will get allocated if no new players will arrive in the future, and you allocate item t according to that current best allocation. Did I lose you? If I lose you, so stop me again. Actually, I liked it when you stop me when something was misunderstood. Okay, and then we have, and then we can think of all the algorithms in between these two extremes, which are all the algorithms which allocate to some player with value at least the value of the player with the current best allocation. So any algorithm that behaves according to this rule is a semi-myopic algorithm, and we have a family of semi-myopic algorithms, and the question is, what is the approximation ratio of each algorithm in the family?
Myopic is semi-myopic on one, basically,
Sorry, can you repeat it again?
So you're saying that the myopic is semi-myopic, where the time that you choose, where the item that you choose is like item 1.
I'm saying that at time, if the algorithm at each time t always allocates exactly to the player located according to the current best allocation, then it is myopic. If he allocates it to some player with higher value, it is semi-myopic. Yeah. And the question is, what is the approximation ratio? Wait a minute, okay. Yeah, sorry.
Because I'm not really understanding the myopic. So at each step, you're just defining the allocation for the current slot.
Yes.
And then
No, not for the current slot, for all remaining slots.
So you do it for all remaining slots.
Yes.
And then the next time
Yeah, you forget about it and do it again.
Right.
Exactly.
Isn't a legitimate myopic allocation going to have put the guy with the highest value in the first slot?
The guy with the highest value in the first slot.
Yes.
Yes, only if, yeah, so if you always just look at the guy with the highest value and allocate to him, then you're back to the greedy.
Right.
But, okay, so you cannot do the switch if the guy with the highest deadline does not belong, the guy with the highest value does not belong to the minimal tight block. You can only do switches inside the minimal tight block. Because otherwise you have to throw somebody out. Okay, so that's why you can't do it. But you can assume that the guy with the maximal value inside the minimal tight block gets. But actually, the algorithm is semi-myopic even if you give it to the guy with the minimal value in the tight block, because he's also in the, yeah. Okay, so it turns out that those two extremes have an approximation ratio of 2, both the myopic and the greedy, but the entire family has an approximation ratio of 3. So any semi-myopic algorithm obtains a 3 approximation. This is the first lemma, and the second lemma, when players are semi-myopic, then both the auctions result in a semi-myopic allocation. So that's the connection, and in fact, if all players are exactly myopic, then the auctions correspond to the myopic algorithm. If all players are completely aggressive about the current item, then the auctions correspond to the greedy algorithm, and any semi-myopic behavior in the middle, so to speak, has a semi-myopic algorithm that is related to it. So that's why we use these names throughout in a confusing way. Okay, so that's about the approximation. Yes?
Sorry, and semi-myopics are going to be something like Set-Nash, so that's the...
Yes, exactly. Yeah. So, the main reason for being so lengthy about the algorithmic characteristics of the two auctions is because somehow I wanted to give you an intuition to the fact that if we don't know anything about the future, we cannot expect to be able to tell the player exactly one strategy that will be their best strategy. There are many strategies, and the best strategy depends on the belief of the player. So we cannot expect to devise some way to tell them play this, exactly this, because we ourselves don't know the future. Instead, what we were hoping to do is to recommend to them on a set of strategies. Each player will choose one strategy out of his set of recommended strategies, and we don't care which strategy he chooses. All of them will lead to a 3 approximation, which is quite good for us. So we define that the strategy sets R1 up to Rn are in Set-Nash equilibrium if the best response to every tuple of recommended strategies of the other lies. So if there is a best response to any tuple of recommended strategies of the other inside the recommended set of player I. So for any strategy tuple of the other, there is a best response in the set of player I. So I have a few comments to make about this definition. First of all, if the recommended sets are all of size 1, then this exactly equals Nash equilibrium. The second comment is a criticism. It says that the definition does not require mixed strategies, the second comment says that the definition does not require that the best response to a distribution over recommended strategies be within the set of recommended strategies. So if I assume that the player plays one strategy, then I have a best response. If I assume that the player plays another strategy, I also have a recommended best response. But if I assume that the players play the one strategy with probability half and the other strategy with probability half, then this definition doesn't necessarily require that the set will have a best response. This is a weak point, but this was all we could prove. This is the second comment. Yeah, so I'll talk about it in a minute. I will. So the third comment wants to note. So I want you to notice that this definition it's not interesting to ask whether there always exists a Set-Nash equilibrium, because a trivial Set-Nash equilibrium always exists. You just recommend all the strategies to all the players. So this is a Set-Nash equilibrium. So it is interesting only if you can achieve some kind of a measure over the quality of the solution if all players play the recommended strategies like we do. That's the third comment. And the fourth comment is that this definition is for complete information games. I didn't say anything about player types and something like that, but it naturally generalizes, so I won't bother to write down the formalities. So that's the comments about the definition. And now I'd like to talk a little bit about stronger definitions. So the strongest definition that one could hope for is the following. Still keeping in mind this notion of a set equilibrium, is this notion of set domination. Let's suppose that the rows are the strategies of player I and the columns represent the strategies of all the other players. So a set of recommended strategies is in set domination equilibrium if for every strategy which is not recommended for player I, there exists a recommended strategy for player I that dominates it, meaning that all the coordinates, so it's larger than it coordinate-wise. So it doesn't matter what the other players play, this strategy is always better off. The player will always be better off with this strategy than in this strategy. This suggests that the player will not choose strategies outside his set of recommended strategies because he can always go inside and increase his payoff in the worst case. So this is the strongest. Okay. Okay, so that's good. That's a good question. So let me. I can answer. I can answer that because I have a picture for it. So in the original definition, the only thing that was required is that for any tuple of the other players, the maximal point for player I is inside the set of recommended strategies.
For any tuple of the other players in their recommended.
Yes, in the recommended. Yes. So the maximal point is always here, but you're not bound to find some strategy like here.
So can I say it like that? That I say, look, I give a certain set of rules. And if I assume everybody else plays by the rule,
yes,
it's best for me to be honest and play by the rule. If I assume some other person is cheating, then I might have the incentive to cheat.
So there are two things that might be bothering. The first is that you assume that all the others play like you want to play. And the second, suppose that they all play like they play, why should I play like I should recommended, like I was recommended to play? So the first part is somehow not that bothering. So I don't know, that's the notion of equilibrium. You assume that all the others act like you think they should act, and then you have to show why I should act according to what I was recommended to act.
Right, so why do you
So the second,
the stronger notion that allows it?
so the stronger notions keep this intuition of set equilibrium, meaning that it's not a single tuple of strategies, but rather several strategies from which you can choose one. But the motivation, why should the players stick to this set of strategies, is stronger. Because here, this is more of a worst-case argument. They don't have to coordinate with the other players.
Sort of goes out of Nash equilibrium. This
Yes.
is saying, like, I'm in Nash equilibrium that I do best even if the others.
Yes, you're right. You're right that Set-Nash goes out of Nash and set domination goes out of dominant strategies, and dominant strategies is larger, more convincing than Nash equilibrium. So that's so.
But you want sort of set dominant.
Yes.
Okay.
Yes. Yeah, exactly. So a definition in between might be the following definition, but of course we don't know. Actually, I have to say that for this stronger notion, we do have a new example, but for this one we don't have an example. But a possible definition might be the following definition: for any strategy outside the set of recommended strategies, and for any belief of player I over the strategies of the others, so for any probability distribution over the columns, there is a strategy inside the set of recommended strategies that is better off on the average, according to this distribution. For any, yeah, something like that. Or for any, I don't know, you can of course change it for any reasonable belief or whatever you.
So why don't you don't have the belief that others play according to this value?
No, you don't, exactly. Because this,
Why don't you define set mixed as I have a set of strategies
Mhm.
and I can choose any distribution in it. And
Any
so
combination.
So now if all other players choose the distribution in their set, then I'm best off choosing the distribution in my set.
so actually,
Why would I care about?
okay,
Again,
no, that's a good question. So why don't I allow mixing over strategies in the recommended set of strategies? So for example, allowing mixing in this case will result back to the set domination. And it's because so that's an observation. So if you allow mixing here, then because of the max mean theorem, or then I can talk about it later. Allowing mixing here is exactly allowing mixed strategies over the set of recommended strategies is exactly equal to results in exactly equals the definition of set domination. Yes.
So this Set-Nash how is this compared to this one?
Sorry.
Is this Set-Nash? It seems like it's stronger in one aspect and weaker in another.
From a Set-Nash, no, it's always stronger than Set-Nash because you can all.
the dominant.
So that's a good question. So if you don't allow mixing over the strategies, then it's weaker because you only want it to be better on the average according to your probability. But actually, that's a good question. I don't know the answer. It's a good question. Okay, so those are the different notions that one can think of, but we were able to prove only for the weakest notion of them all. And the theorem that we have is that both our auctions, the online iterative auction and the sequential Japanese auction, both have a Set-Nash equilibrium so the online iterative auction and the sequential Japanese auction, Set-Nash implement a three approximation of the welfare, meaning that they both have a Set-Nash equilibrium that is all semi-myopic, is composed of all of these strategies are semi-myopic strategies, and therefore it guarantees a three approximation.
Do you have examples in which they use this strategy outside?
Yes. Yes, I have. For these two auctions I have one other mechanism in the paper for which I don't have an example. So I'm not, but for these two auctions I have examples, yes. I'm still somehow believe that you can construct a mechanism that has a set domination for this problem. So I'm not all pessimistic about it, but for these two auctions I do have an example.
What if so I have many players, let's say. What if I assume that maybe one or two don't play by the rules, but the majority plays by the rules? Can one then sort of show that I don't lose too much? Because it may be assumed that
that's
too
a good.
much that nobody,
Yeah.
maybe there's one cheater.
Yeah, actually, that's a good direction. I didn't think about it at all. So, yeah.
Because I mean, then I would be willing to play by saying,
Yeah, I know. Yeah, that's a good point. I don't have an answer. That's a good direction. Yeah. Okay, I have few remarks about this theorem. First of all, the recommended strategies are not dominated, so that's a good thing. And also another good thing is that the recommended strategies contain best response, even if the strategies of the others are taken from a larger set. But the weak point is that the recommended strategies do not necessarily contain best response to mixed recommended strategies of the others. So this is an interesting problem.
There are many recommended strategies.
How to choose one of them.
One of them is very good and all the rest are terrible.
Yes.
You don't know which one to choose. Maybe you're better off not taking any recommended strategy. Just take something else with mistake.
Yes, this is.
Good, but not very good.
Yeah, so this is the criticism over the Set-Nash notion. So you're right. Yes, you're right. Yes, you're absolutely right.
So let's say of the recommended strategies, one is very good one, and all the rest are the worst one. You don't know it. So when you pick a recommended strategy, you are very likely to take a very bad strategy. Because if you take some other strategy that is not recommended, I think you have higher probability and you start with something good. Okay.
So that's exactly the reason why we included a discussion about stronger notions. For example, in the middle notion, for every belief that you have about the distribution over the others, so about how bad this strategy will be or how bad that strategy will be, for every belief that you have, it's not better off for you to deviate from your set of recommended strategies. Because if you have a belief and you are thinking about taking this strategy, then you can find a good strategy inside, a recommended strategy, that is better off on the average according to your belief.
Wait, you can find a good strategy or probability?
No, a good strategy. Yeah, and then if you can find the probability of strategies, it even makes the problem more difficult.
But how do I find the probability?
How do you find it?
Or is, sorry.
So how do you, so that's
Then
a,
it's the same problem. I have to assume the probability
Yeah.
the others which I don't know.
you don't know, but of course, if you choose some other strategy outside, you also choose it according to some belief of yours over what will happen, what the others will do. So if you also,
Maybe much more I mean, this has still your problem.
yes. No, the set domination hasn't got Uri's problem because
Because suppose every element that I choose, for example, there is one strategy that I can choose outside the set. There are strategies inside the set that are dominating that strategy, like say a factor of n.
yes, but suppose
But any strategy that I choose from the set will be dominated by another strategy in the set very bad. So if they all have a very bad weak point, there might be something outside the set that has a very weak.
But suppose that you go over this iterative process in your mind and you come up with a strategy which is a blue strategy outside. Then I can show you a strategy inside which is better off always. So do your thinking process, your mentally thinking process. Come up with any strategy you like. Any. Then I will be able to give you a strategy inside that it's completely better off. So you won't have any reason to deviate from the
But
inside.
you didn't tell me that you give it to me. Because you can only give it to me if you know what the other
You're right. So I didn't tell you. I
don't
didn't.
know what the other
I did.
No, he's talking now about domination.
Yeah, which is not what we did in this paper. Yes.
They
Yes.
would like, that's why they like that.
Yes.
Because this just says that for every play,
For every blue strategy,
no, for every strategy of the other, whether it's recommended or not.
the orders of quantifiers. For every blue line, there's a brown line.
Exactly.
Point-wise.
Yeah, coordinate-wise, yes.
So this is why you would like this.
Yes, this is why we would like this, yes. This is why we were very sad we didn't manage to do that.
Right.
But this is why we included it anyway, because of a criticism like Uri gave, which is a very good criticism.
Right,
So in
right.
fact, you would like something stronger that you can actually compute.
Yes, yes, yes. I didn't write a full definition because, we don't have it here, so to be bragging too much to write a full definition for something we don't have yet. But, yeah.
I'm trying to come up in my head with a really bad semi-myopic strategy.
So I'll be happy after the talk to show you an example. I have to think about it a little bit myself because I have to reconstruct it again. But there is one example, yeah. But I have a strong feeling that I missed something. So we missed something. I don't know. So you're right that there should be. It seems that there should be some kind of a mechanism that will admit this set domination notion. But yeah.
We are essentially changing the model so that the edges can interact with the mechanism. Interact with the particular.
Why do you say that?
I mean, like you have a mechanism that changes the size of people.
Yes, yes, yes.
So now, if you go back to the simple model, where people only submit their arrival and departure time, and you put a proxy for it.
Exactly. Okay.
Would you be able to get a Set-Nash for this one?
Yeah. So that's a good question. So actually, I have an answer in the slides. I will continue. You should just stop me whenever time runs out. I have about 10 to 15 minutes more. I don't know.
So why don't you outline for us what you could do in that 10 to 15 minutes and then change something? Or you just want to go linearly and we at a certain time say,
Want to do this?
I just no.
East or English?
No. The only thing that I want to do is to give some intuition to the proof of the main theorem. How do we prove the main theorem? That's the only thing that I want to do. But if time ran out, I can.
Maybe you can say something about the concept question. Whether there are other ways of implementing it,
yeah.
other than having them participate and interact with the other.
Let's do English. Erase some parts.
Yeah, so the way that I'd like to say it is by giving you intuition to the main theorem, because actually the way that we prove the main theorem is by using something related to Muhammad's question. So that's why I'd like to give you intuition to the proof of the main theorem. I think it will be helpful. It will be very related to Muhammad's theorem. So the way that we prove the main theorem is according to the following picture. So initially we don't prove nothing about both our options. Instead, we define some mechanism which is almost a direct revelation mechanism, and we prove all the properties to it, on it, and then we show the connection between this mechanism and the two auctions. So we show somehow that it is embedded, loosely speaking, in the two auctions. So, and this basic building block has exactly the same intuition as what you asked. So players reveal their true parameters plus some additional information, so let me tell you about it. So just let me refresh your memory about all the definitions. So we had this basic structure of allocations. Now, because we're in the online case, we have to add this parameter t. So we denote by st the optimal allocation at time t. So that's the current best allocation at time t. And ft for first t is the minimal tight block at time t. And we had again the highest unallocated player I star. And I just want you to remember that if players are myopic, then at time t, both the auctions compute the optimal allocation, the current best allocation. Because you can think of it as it is an offline case at time t. Yes. Yeah, no arrival times there is. So this is exactly the offline case in which all players arrive at time 1, so to speak.
AI is identical.
Yeah, all the AIs are t, or 1, which is, yeah, whatever, yeah. Yeah. No, so this is what happens at time t. So at time t, you have ST, which is optimal allocation at time t. You have FT, which is optimal at time t.
So for all intents and purposes,
Yes.
it may as well
Yes.
all arrive at
Yes.
T.
Yes.
This is whoever's
Yes, exactly. And then if all players behave myopically in this period, then both the ascending auctions compute the FT and the VCD prices. Okay, so this basic building block of a semi-myopic mechanism is defined as follows. So don't be intimidated by the many words that are on the slide. The strategy space of the mechanism is what we call an extended direct revelation mechanism. The player is required to tell his arrival time, his true arrival time, his true value, and his true deadline. And in addition, he has to also declare a false deadline between his arrival time and his true deadline. So we require from him to reveal his true parameters plus an additional information that somehow is supposed to capture the degree of freedom that he has in choosing a semi-myopic strategy. So if the false deadline is very close to the arrival time, he will, so to speak, act in a very aggressive way. And if the false deadline will be close to the true deadline, then he will act more myopically. And then the mechanism will compute the optimal allocations ST at each time t according to the pretend deadline of the player, which is his false deadline if this has not passed yet, and his true deadline otherwise, and will allocate according to this optimal allocation ST. And also the payments will be according to VCG. So that's the semi-myopic mechanism. And the recommended strategies that will form a Set-Nash equilibrium are declaring actually the true parameters and any false deadline between the true arrival time and the true deadline. And we have two lemmas that says that if all players play recommended strategies, then this allocation rule results in a semi-myopic allocation. So we have a 3 approximation. And the second lemma says that these recommended strategies form a Set-Nash equilibrium. So if all the players act like this, then I have a best response in this form. And so that's the analysis of this semi-myopic mechanism. And I won't get into details about it. I only want to explain why this building block can be viewed as embedded inside the two auctions. But this is actually very simple. If the recommended strategies for both of the auctions is just to choose a false deadline in between your true arrival time and true deadline, play myopically until this deadline, and play myopically with the true deadline afterwards. And because those two auctions compute okay, yeah, that's clear, great. So that's it. Actually, I was exaggerating about actually it was 10 minutes. Yeah, so let me just summarize to get you back to the global picture. So we study an online setting with gradually expiring items. And the first thing that we show is that truthful auctions are not possible. Deterministic truthful auctions are not possible. And then instead of putting limitations on the players or assuming strong distributional assumptions, we explored a new approach. It is a worst-case approach, no additional assumptions. We analyzed, in order to achieve positive results, we analyzed two adaptations to classical ascending auctions. Both of them obtain a 3 approximation under a large family of selfish behaviors. And then we try to analyze why should the players behave in such a way. We introduced the notion of a Set-Nash equilibrium and showed that both our auctions have a Set-Nash equilibrium which guarantees this approximation. That's it.
Yeah, I mean, we've asked you a lot of questions.
Yeah, okay.
We have tea, so we can ask
Okay.
you offline. We know offline is
Now,
easier,
yeah.
right?
So how do I stop the...
Oh, yeah.